organization. Please join me in welcoming to the Distinctive Voices podium, Dr. Alex Filippenko.
Well, thank you very much, Susan, for that very warm and kind introduction. And I'm happy that you're all here. Was everyone able to get in, even in the standby line? Yes, excellent. Well, it's good that there were some no-shows, right? Anyway, it's a great pleasure to be here this evening and to have been asked to speak as part of this wonderful Distinctive Voices series. I'm really quite honored to be here. So my talk tonight, of course, is on astronomy, but more specifically, it's on cosmology, kind of a subfield of astronomy that deals with the structure and evolution of the universe as a whole. So we're really interested in some of the grandest, deepest questions that humans have ever considered. How big is the universe? Is it finite? Is it infinite in size? What is its shape? Does it wrap around itself somehow like a beach ball, or is it shaped like a torus? Is it infinitely old or of finite age? And in fact, here you can see that this was the cover of Time magazine. When did the universe begin? You could call this a big time story. You see that, a big time story. When did the universe begin? Well, a crowning achievement of the past century is that physicists and astronomers have, through measurements and theory, figured out that the universe is about 14 billion years old. A very long age, but nowhere compared to infinite, okay? So it's about 13.7, 14 billion years old. Similarly, what will the fate of the universe be far, far in its future? Many of you know that it's expanding right now. That'll be the subject of my lecture. Will it continue to expand forever, or will it someday reverse its motion and collapse in on itself? Another big time story. You see how the universe will end. Well, this cover story was written in June of 2001 on the work that our team did. And at that time, a decade ago, we thought we knew how the universe would end. Now, a decade later, we know more, and we now understand that we don't know how the universe will end, but we have a couple of possibilities, and that's what I'll describe for you today. But anyway, they really should have had a question mark here. How will the universe end? Okay, and we definitely have not yet solved the biggest mystery in the cosmos. Cosmologists are also interested in the basic building blocks of the universe, and those are the galaxies. Galaxies are giant, gravitationally bound collections of tens or even hundreds of billions of stars. We live in one such galaxy, the Milky Way galaxy. We can't see it from the outside as we do this galaxy, but we think that if we could view our galaxy from the outside, it would look something like this one. A giant collection of stars about 100,000 light years across. So if you were on a planet orbiting a star here and you sent a message to your alien friend on a planet over there, hey, let's go to the Distinctive Voices program, it would take 100,000 years for your signal to reach that alien and another 100,000 years for the reply to come back. Gee, I tried to log in, but the tickets were sold out. Yeah, as apparently happened within 10 or 15 minutes after this program tonight was announced. I'm very pleased with that, but anyway, and I'm glad everyone was able to get in. Anyway, so a 200,000-year conversation is hardly a stimulating conversation, but I'm sorry, that's just the way the universe is built. I'm just the messenger, okay? And there are many such galaxies. Indeed, we see them all over the place. Here's one of my favorite photographs from the Hubble Space Telescope. This is just part of what's called the Hubble Ultra Deep Field. The telescope stared at one patch of sky for nearly 2 weeks. And it's a tiny patch. If you imagine a small pebble or a large grain of sand held at arm's length, that's about the fraction of the sky covered by this photograph. Yet it's filled with these little fuzzy galaxies, something like 2,000 or 3,000 of them in this photograph. You see 1, 2, 3, 4, 5. I could spend my whole hour counting galaxies. That wouldn't be very interesting for you, but it's kind of interesting to me that they pay us to do this kind of stuff. Okay. Anyway, don't tell too many people. The field is overcrowded as it is. Anyway, if you extrapolate over the whole sky, you can figure out that within the realm of today's greatest telescopes, There's something like 100 billion galaxies, and that's just in the parts of the universe that we can see. We now think that the universe extends far, far beyond just those parts that we can see, and everywhere it's filled with these galaxies. So how do they form? How do they evolve with time? These, too, are among the central questions of cosmology. So you can see that we grapple with some of the grandest topics imaginable. Now, before I move on, let me point out that among the lay public, present company excluded because you're well educated and come to these Distinctive Voices lectures, but among the general public, there's considerable confusion between cosmology, the study of the structure and evolution of the universe as a whole, and cosmetology, the study of hairdos and facials. Now, they sound similar, I admit. They're even spelled similarly, although if you write them down, cosmetology is cosmology with an extra ET, like the extraterrestrial. Write them down. I don't know the cosmic significance of this extra ET, but that's the only way in which their spellings differ. Now, of course, like astronomy and astrology, which sound similar and have common roots, they've bifurcated quite a bit. But to give you an example of this confusion, here's a copy of an ad that a colleague of mine placed in my mailbox a few months ago. Make cosmology your career. Training and supervision in hairstyling, blow drying, permanent waves. You laugh, but these are all very important topics, okay? Coloring and frosting, scalp treatments, body and skincare, scalp cuts, basic cuts. For further information and interviews, call that number. Now, classes started a couple of months ago, so you're too late. But I'm sure that they'll hold them again in the summer session or next fall, so you can take them, which you should do if you want to do, as I and some of my colleagues have done, and get to the cutting edge of this field. I know, this is bad, okay? You only have to put up with me occasionally. My students put up with me every other day. But seriously, these guys need a lesson not only on what their own field is, but a lesson in spelling and proofreading, because in addition to foother here, you see hair slying. See that hair slying? And coloring, well, that's the British spelling, and my own thesis advisor was British, so I'll allow that one. Anyway, it's kind of funny. They don't know their own field. Actually, this reminds me of a joke that my father-in-law came up with. He says, Alex, the only real difference between your Berkeley course on cosmology and a course on cosmetology is that you don't give makeup exams. Oh, my goodness. So, yeah. Okay. No, that's Gary Edwards, my father-in-law. So, let me get a little bit to the science. It starts with an interesting fellow named Vesto Slipher, who in the teens of the last century examined these galaxies, a whole bunch of them, and their nature was not yet known. They were called spiral nebulae at that time, and people didn't really know whether there are other galaxies like the Milky Way or clouds within our galaxy. But he took spectra of these objects. He passed the light, here it says sunlight, but you can take galaxy light, pass it through a prism, disperse it into a rainbow, a spectrum like this. And this procedure, spectroscopy, is something that all scientists use to understand the object that they're studying. And in particular, if you take the spectrum of a star, you can figure out its chemical composition. These lines here are due to sodium atoms in the atmosphere of the star. These are due to ionized calcium. There's hydrogen there. So you can tell the composition. You can tell the temperature of the gases, the pressure of the gases, the density, all sorts of good stuff. The spectrum also tells you whether the object is moving toward you or away from you, and by how much. And this is essentially the Doppler effect. You've all heard this audibly. When you hear a siren coming toward you, the pitch sounds higher than when it's at rest, and when the siren is going away from you, it sounds lower. And that's because when it's coming toward you, the wave crests are squished together. The object moves some distance in between the emission of two successive wave crests. So the wave crests are closer together, the wavelength is smaller, the frequency is higher. And conversely, when it's going away from you, the wavelength is longer, the pitch is lower. And by measuring the shift in the pitch, you can figure out the speed. So you can hear the siren go like that. Now, if you hear a siren going ee-ah, 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 it doesn't mean that the driver is drunk and can't make up his mind which way to go. It just means that the pitch of the siren isn't constant. But if you listen carefully, you can hear the high-pitched ee-ahs go to low-pitched ee-ahs. And what Slipher observed was that almost all galaxies have spectra that are shifted toward longer wavelengths, toward the red. This is a redshift, indicating perhaps that these galaxies are moving away from us, unless there's some other explanation, but we've not found another explanation in 100 years. Hubble then took Slipher's data and went one step further. Hubble measured the distances of the galaxies whose spectra Slipher had measured. And Hubble, after whom the Great Hubble Space Telescope is named, of course, made an amazing discovery. He noticed a correlation between the amount of redshift and the distance of the galaxy. And this holds for all but the nearest galaxies. A few galaxies, like the Andromeda Galaxy, are so near to us that they're gravitationally bound, and in fact, the Andromeda Galaxy happens to be moving toward us right now and has a blue-shifted spectrum. But if you go outside our local group of galaxies, there's an interesting correlation. They're all moving away, but right now, at a given time, the more distant galaxies, which generally look smaller and fainter in the sky, are moving away from us faster than the nearby galaxies, which generally look brighter and bigger. So they're all moving away, but the more distant ones are moving away faster than the nearby ones, okay? So here we are, the Milky Way galaxy right there, and all these other galaxies are moving away, and right now, at a given time, the more distant ones are moving faster than the nearby ones, as indicated by these arrows. So the universe, it turns out, is expanding, and Hubble resisted this particular interpretation of the redshifts at the time, but we now actually know that space itself is expanding. It's not even that the galaxies are like little bullets moving through a pre-existing space. We can actually tell that space itself is expanding. It's like a coordinate grid, and you've got all these tick marks, and the tick marks, which are the galaxies, are getting apart farther and farther apart from one another. But the galaxies themselves aren't expanding because they're gravitationally bound. So before discussing this a little bit further, let me point out that there's something a bit strange about this diagram as I've drawn it. What's strange about it? Yeah, we're at the center. You know, why should that be? You know, do the other galaxies not like us? Is it something we said, or do we smell? Are all these other galaxies lactose intolerant? Get it? Milky Way galaxy, lactose intolerant, yeah. When I talk about cosmology at my home institution, Cal, I say, you know, are we from Stanford or something? You know, big rivals. Here it could be UCLA, USC, you know, or Irvine. I'm not sure who the main rival of Irvine is, but whatever. No, we don't think that we're in any special position, okay? We think that regardless of which galaxy we happen to be in, we would see all the others moving away from us. In fact, that's a property of a uniformly expanding universe. And let me give you an example. Here's a loaf of raisin dough where the yeast has been spread uniformly through the dough, and you let it bake for a while, okay, let's say an hour. And again, don't worry about the edges. The universe is either infinite or it wraps around itself. That was hard to draw here, so I have finite edges, but I'm not trying to trick you. And the raisins are the galaxies. They don't expand. They don't have yeast in them. The galaxies are gravitationally bound. But you can see that from the perspective of this raisin, all the others moved away. But the same can be said from the perspective of this one here. All the others move away. So they can call each other up and say, hey, I'm the center of the universe. And the other says, no, I'm the center of the universe. But in fact, none of them is the unique center. Indeed, you can even see Hubble's proportionality. This raisin here started 5 centimeters away. After 1 hour, it's 10 centimeters away. By advanced mathematics, 10 minus 5 is 5 centimeters. Average speed, 5 centimeters per hour. This one started out 10 centimeters away. After an hour, it's 20. Its average speed was 10 centimeters per hour. The more distant raisins from any given raisin move faster. That's because every bit of dough expands. And so if each centimeter turned into 2, then the more centimeters you had to begin with, the greater will be the total extra distance covered, and so those objects move faster. It's not because they're accelerating. This is not yet the evidence that I'll be talking about in a few minutes. This is just evidence for an expanding universe that's uniformly expanding. Okay, so with telescopes like the Hubble, we now have measured the expansion rate pretty accurately. It's some number. For those who care, it's 71 or 2 kilometers per second per million parsecs. Don't worry about that if that's meaningless to you. It's just some number, okay? And you might think, okay, the work of cosmologists is done. But that's not true, and this goes all the way back to Newton. Newton studied gravity. He supposedly saw the apple fall from the tree. It didn't hit his head. That's apocryphal. But anyway, you can't give a talk about gravity without using the proverbial Newtonian apple, so here it is. If you toss the apple up, then the mutual gravitational attraction between the earth and the apple slows it down. And in fact, it eventually stops and comes back down. And even if I throw it a bit faster, it will do that. So in a similar way, all the galaxies should be pulling on one another. So if the density of the universe is high, that is, if there's a large amount of matter per unit volume, then every unit volume is going to be pulling on every other unit volume quite a lot, slowing down the expansion until it stops and then reverses itself, just like this apple, okay? So you could say then that this is the Big Bang, and then you'd get the Big Crunch sometime later, billions of years later. Big Bang, Big Crunch. Or you could say Big Bang, Gnab Gib, which is Big Bang backwards, okay? Big Bang, Gnab Gib. So if the universe is sufficiently dense, then the current expansion will someday stop, reverse itself, and the universe will end with this big crunch. On the other hand, it's also possible that had I eaten my Wheaties this morning, and if there weren't the technical difficulty of a ceiling here and a roof, I could heave this apple so fast that it would never stop, and it would never reverse its motion. It would keep on going away from the Earth forever. That's a speed greater than the escape speed, or equal to the escape speed, about 11 kilometers per second. And in fact, in that case, the apple never comes back. On the other hand, it does continue to slow down, right, with time. It just never comes to a stop. It asymptotically approaches some constant non-zero, or in the case of the escape velocity, zero velocity. And so, but it never turns around. So if the density of the universe is sufficiently low, then okay, maybe all these galaxies are pulling on all the others, retarding the expansion, but the expansion might continue forever, like this apple thrown at a speed equal to or greater than the escape speed. In that case, the universe would expand forever, becoming ever colder, darker, more dilute, a very different fate than the Big Crunch, okay? So here you see this coordinate grid continuing to expand. It's expanding more and more slowly with time, asymptotically approaching some constant speed, or a zero speed if you threw it at exactly the escape speed. So cosmologists would like to know which fate the universe is going to suffer, either a recollapse or eternal expansion, okay? And you can tell by measuring the past history of the expansion. After all, if I were to measure the trajectory of the apple at certain instants of time, a few of them, and see that it's been slowing down a lot, then I could predict that it'll someday stop and reverse its motion. But if I measure it and I find that it hasn't been slowing down very much, then you can figure out that it'll keep on expanding forever. So we can examine the past history in order to, at least in principle, predict the future of the universe. And you might say, okay, we measure the current expansion rate now, but how are we going to compare that with anything in the past? We can't measure it in the past, can we? Because we live right now. But it turns out there is a way of measuring it in the past. Anyone want to venture a guess? Yeah, a bunch of people said it. Far away. What's your name?
Lorna.
Pardon?
Lorna.
Lorna says, look at things that are far away, because it takes time for light to get from there to here. So you're looking back into the past. In fact, here's a fun fact. Light travels about a foot per nanosecond, a foot per billionth of a second. So I'm seeing Lorna as she was maybe 30 billionths of a second ago, not as she is now. She may not even exist anymore. She does. Good for her. She's still on this good earth, okay? You see the sun as it was a little over 8 minutes ago, because it takes 8 minutes or 8 1/3 minutes to traverse 93 million miles, 150 million kilometers. Even the typical brightest stars you see in the sky are some tens or hundreds of light years away. So you're seeing them as they were tens or hundreds of years into the past, okay? Not as they are right now. And if you look at galaxies that are 1 billion light years away, and maybe that one's 4 billion light years, and maybe that little smudge there is 9 billion light years away, then you're seeing them as they were 1, 4, 9 billion years ago. And encrypted in the light from those galaxies is information on the expansion rate as it was 1, 4, 9 billion years ago. So you can make a movie, in a sense, of the expansion rate over time, and thus predict the future. That's the idea. But you need to know exactly how far back you're looking. Is that 4 billion light years away, or 3.7, or 4.6? You've got to have a way of determining accurate distances of galaxies. How do we do that? Well, for nearby galaxies, it's relatively straightforward. Here's a beautiful Hubble photo where you can see the individual stars, okay? Let's just focus on that one there. Let's just call it Susan because she introduced me, so that star is Susan. And let's say that through spectroscopy of that star and other studies of that star, we can tell that Susan is just like this brilliant star in Orion the Hunter, okay, Betelgeuse, all right? Not all the stars are the same. They come in different categories, and you can determine this through detailed studies. Well, Betelgeuse is relatively nearby, and we can measure its apparent brightness, and from those two quantities, we can determine its true power. And it turns out Betelgeuse is a very luminous, powerful star, okay? And if we know that Susan is just the same kind of star, then we can compare the apparent brightness here of the star with the true power, the wattage, the luminosity of Betelgeuse, and thus determine that star's distance. And if you do this for a bunch of stars in the same galaxy and you get the same answer, then you've got pretty good confidence that you're doing the technique correctly. And, you know, this is simply based on something you do all the time when you judge the distance of an oncoming car at night. You know how bright the headlights of a nearby car are. So you take a car that's 6 feet away and you look at the headlights, they're really bright, and you know the distance. That kind of calibrates things for you. And then when you look at more distant cars, you see that the headlights are fainter. And your brain almost instinctively, almost intuitively makes this little calculation of how far away the car is. It also uses the apparent angular separation between the headlights, by the way. That's a consistency check. So you're doing this all the time at night. In fact, if you're not very good at this, then you shouldn't be driving at night, okay? But cars, stars, it's the same principle, all right? We use the inverse square law of light. Okay, you might say that works fine for nearby galaxies in which we can see individual stars, but what about these galaxies here where, you know, there's billions of stars there, but they're too faint to see individually, and they merge together, all right? So you can't distinguish individual stars from their neighbors. So you might think you're hosed. But it turns out there is one type of star that can be seen and distinguished from its neighbors billions of light years away. What kind of a star is that? Supernova, that's right. The introduction, I think, probably gave it away. A supernova is an exploding star. See that? There's the star before it exploded, and there it is after it exploded. Only a small minority of stars do this, okay? But those that do can become up to a few billion times the power of our sun. So in fact, here's a galaxy in which a star blew up. I've sped up the procedure here, okay? It actually takes a couple of weeks to brighten and many months to fade. But here at its brightest, it was as bright as the central billion stars in this galaxy. And yet that was one star blowing up, okay? So they're really powerful, a billion suns. If our sun were to do this, and don't worry, it won't. It'll die much more quietly. But if it were to do this, then sunblock of 50 just wouldn't cut it, folks, okay? You'd need sunblock or supernova block of 1 billion in order to protect yourself from this gargantuan explosion, okay? But don't worry, be happy, our sun isn't going to do that. It's gradually getting brighter. That'll cause much more severe global warming in about 100 million years or so. But anyway, you look at these things and you can calibrate them in nearby galaxies. So suppose we find some of these headlights in a galaxy of known distance. So we can see normal stars in this nearby galaxy. So we've already figured out the distance of this galaxy, but we measure the peak brightness of the supernova. Well, just like with Betelgeuse, if you know the distance and you measure the peak brightness, that allows you to calibrate the luminosity, the power, the wattage of your light bulb. So you want to find these things in nearby galaxies and calibrate them and see if there are different types of explosions. Indeed, there are different ways in which stars can explode. Some are better light bulbs than others. They're more standard. They're more uniform. You don't want to use the light bulbs that always differ from one another, okay? But you have to measure a bunch of these guys in nearby galaxies to establish their luminosity and how uniform they are. But unfortunately, exploding stars are pretty rare. in a galaxy like this, a star might explode once or twice in a century, okay, maybe 3 stars per century. So if I were a really cruel advisor, I would have each of my students staring through the eyepiece of a telescope, preferably at night. You see more stars and galaxies at night. Staring at one and only one galaxy until that student finds a supernova, then they get to graduate and move on to greener pastures. Meanwhile, I will have had decades of slave labor from this student. Well, some crimes are so egregious that even a tenured professor can get fired, and this would be one such crime. Students, of course, need to study and sleep, and most importantly, party, and so it would be cruel and unusual punishment to make them stare through the eyepiece of a telescope like this. But there's power in numbers. After all, one supernova per galaxy per century, just for round numbers, is statistically the same thing as one supernova per 100 galaxies per year. Each of those 100 galaxies will produce a supernova sometime in the next century. You just don't know when. That means on average, one of them will do it in any given year, right? So if you monitor all of them, you'll catch it. If you monitor 1,000 galaxies, you'll get 10 of these supernovae on average, okay? So I could have my students staring through the eyepiece of a telescope at thousands of galaxies looking for supernovae, but that would be considered cruel and unusual punishment as well. Instead, astronomers use different techniques, not just humans. They use advanced technology like the CCD cameras that you have, your video cameras or your electronic cameras have charge-coupled device detectors. You stick these things at the back end of telescopes and you take photographs of thousands of galaxies. This replaces the eyeball, okay? You take photographs of thousands of galaxies and you simply look for arrows. And where you see arrows, you see an exploding star. Once, twice, 3 times, 4 times, 5 times. By rigorous mathematical induction, I conclude that this procedure must work every time, okay? Well, obviously, it's got to be a bit more complicated. Otherwise, we wouldn't give degrees for this kind of work. Astronomers have been doing this now for decades, taking photographs of galaxies, and you can either compare the photographs, the old ones and the new ones by eye, or now we can write software that does this. And in fact, my team has been, for the past 12 years or so, using a robotic telescope that takes pictures of galaxies roughly once a week. So it goes through almost 10,000 galaxies in a week, because it does over 1,000 of them a night. And it automatically takes those pictures. It's got a CCD camera mounted down here. And it automatically compares the new pictures with the old ones, okay? And it comes up with supernova candidates. And so here's an example of a supernova candidate. Oh, actually, this is, sorry. This is Wei-Dong Lee, an associate of mine who deftly programmed this, this computer to do all this, the telescope to take all these exposures and to do the automatic comparisons. Anyway, he's a very, very valuable member of my team. And this thing, there's the candidate. There was a little glitch in my system there. But here's an old picture of the galaxy, and here's the new picture. And you can see that there's this arrow here. But no, actually, there's this thing here. And we mark it with an arrow using Adobe Photoshop or something. But anyway, this is a supernova candidate. We don't know that it's an exploding star, but it might be. It also might be a cosmic ray, a charged particle that hit the detector and masquerades as a star. Or it might be an asteroid that has Earth's name written on it as it's flying through space. You know, the killer asteroids. If there hasn't been a talk as part of this series on this already, there should be at some point. But yeah, they're out there, and astronomers are scanning the sky to find them. We'll be the ones who hopefully find this object well before it hits, and then the engineers will figure out a way to deflect it somehow. So astronomers will someday hopefully save humanity. Anyway, there's maybe 50 candidates per night out of these 1,000 images or so that we take. So then I use students who, with their brain-eye combination, examine the different candidates and determine which ones are likely to be exploding stars and worthy of follow-up observations. I'm very proud of my team. A close-up of this fellow at the left is shown here. I don't know if he's trying to get a date or what with that hairdo, but remember, I'm from Berkeley, okay? So not quite the same as Orange County. But anyway, so I'm very proud of my team. I have a weekly team meeting where I bring them pizza, and they justify their existence for the past week. So The robotic telescope, and Wei Dong and my team of undergraduate students have been, as Susan mentioned, the world's leaders in finding exploding stars for roughly the past decade. Now, admittedly, the past year or so, there are other surveys with wide field cameras that are able to cover much more of the sky, so they see more galaxies. They're now beating us. But we had a good run for a decade there, and we're still using this telescope more so now to study the supernovae. But notice I didn't put 2010 here because our numbers were lower than those of other surveys. But anyway, we've done very well. We found the first supernova of the new millennium, regardless of your definition of the new millennium. See that? And our first supernova was in 1997. That was hardly a world record. And you might think it was a supernova of questionable integrity, given its name, 1997 BS. But they're named in order of discovery in a given calendar year. A, B through Z, you know, A, B through AZ, and then BA, and so on. So I'll leave it as a relatively uninteresting exercise for the listener to figure out what number that was. But we find a bunch of them and we study them. And we and other astronomers, I don't want to imply that we're the only ones who have done this, but over the decades, astronomers have categorized the different kinds of supernovae and figured out how powerful they are and which ones are the most standard, okay? And in particular, here's a nice exploding star, dutifully marked with an arrow, and you can study such stars through spectroscopy by collecting the light with a bigger telescope, okay, and spreading the light out into a spectrum like this, plotting brightness on the vertical axis versus color or wavelength on the horizontal axis. You come up with the spectra of supernovae. And for a couple of decades now, it's been known that there are two main classes, those that don't have hydrogen, the type 1s. That's interesting because hydrogen is by far the dominant element of the universe. These have lots of other stuff. Look, the spectrum kind of looks like a roller coaster. But interestingly, they don't have hydrogen, nor do they have helium. And then there are the type 2s that do have hydrogen. Now, look at all these other elements here: oxygen, calcium, silicon, sulfur, iron, magnesium. These are the elements of which Earth, and to some degree humans, are made. I mean, humans are mostly water, so mostly hydrogen, but we certainly need heavier elements to live, to be alive, right? And those heavy elements were produced inside stars billions of years ago. And the stars that explode, that small minority of stars that explode, eject these elements into the cosmos. And during the explosions, make some of the elements as well. And those elements then become the raw material for new stars, planets, and ultimately life. So this is what Carl Sagan meant when he used to so eloquently say, we are made of star stuff, we are made of star dust. And you can see the evidence right there. I mean, the argument is more involved than that, but I don't want to take the time right now. Nevertheless, if you don't like cosmology, if there's one thing to take away from tonight's lecture is you can tell your neighbor, you know, we're made of star stuff. Quite literally, the carbon in your cells, the oxygen that you breathe, the calcium in your bones, the iron in your red blood cells, all those elements were produced deep inside the nuclear furnaces of stars billions of years ago. Some of those stars exploded, and then 4.5 billion years ago, those ejected gases got incorporated into what we call the solar system. It formed about 4.5 billion years ago. Okay, well, among the type 1s, there's a subcategory called type 1a, which we've found, we and other astronomers have found are the most uniform and generally the most brilliant type. And they're pretty uniform because they come about from the explosion of a star called a white dwarf. It's a weird kind of a star. Our sun will turn into a white dwarf in about 7 billion years, but our own sun, won't explode because it doesn't have a companion. But those white dwarfs that do have a companion can steal material from the companion, and that material piles up on the star and increases the mass of the white dwarf. And at a certain limiting mass, the white dwarf blows up. It's a gigantic thermonuclear runaway, because the matter out of which the white dwarf is made is called degenerate matter, not because it's morally reprehensible or anything like that. It's just a term that quantum physicists give to matter that's very, very highly compressed. And at a certain mass, about 1.5 times the mass of the sun, it turns out the electrons, the degenerate electrons, are no longer able to hold up the star, and the nuclei in the center of the star start fusing, generating energy, and that causes an uncontrolled chain reaction of the other nuclei there, and the whole thing just goes off in a flash. of about a few billion solar luminosities. And they're pretty uniform because they all go off at about the same mass in a pretty uniform way. Now, they're not all exactly the same. It's just like not all light bulbs are 100-watt light bulbs. Okay, they vary, 50 watts, 150 watts. But there's a way in studying these supernovae where we can read the label on the light bulb and tell individually what wattage each of them has. And some are 120 watts, some are 92. Of course, much bigger than that. I'm using typical light bulbs just as an analogy. So we've calibrated these things quite well. And this has been work that's been going on for decades now, this calibration business. Okay, so we now know how luminous they really are. Now let's go and find them in distant galaxies, use the inverse square law to judge their distances, and thus know how far back in time we're looking, and thus trace the expansion history of the universe. Okay, so now I'm going back to what I described near the beginning. So, almost 2 decades ago, 2 groups formed. Here's one of them. I was actually a member of both groups for a while, but my primary allegiance was with this one, the High Redshift Supernova Search Team, led by Brian Schmidt of the Australian National University. And the other team was led by Saul Perlmutter at UC Berkeley. It's called the Supernova Cosmology Project. And here's Saul and here's Brian. They weren't always at each other's throats. Here we are, in fact, in Aspen. We would get together occasionally to discuss our progress and our techniques and stuff. And it was good to have 2 teams because, both wanted to be first. There's the competitive spirit among scientists as well as among Olympic athletes or other, professions. And both wanted to be best. So if one team were taking into account something subtle and the other team were not, then that other team would look bad by comparison. So it improved the quality of the science, and it definitely made us all work harder, okay, in the 1990s to get to the result. Both teams came up with the results I'm going to tell you about at about the same time. Both teams used telescopes primarily in the southern hemisphere. This one is an observatory in Chile, to take pretty wide-angle pictures of the sky. And by wide angle, I mean about the size of the full moon. For a big telescope, that's a wide angle, because usually big telescopes look at just a tiny patch in the sky. But this is a patch that's about the size of the full moon, and this is a deep exposure. And in this picture, you see literally thousands of galaxies. Nearly every blob here you see is a galaxy. You rapidly run out of stars in our Milky Way if you take a deep enough picture showing faint things. So all these little blobs are galaxies. And if you take a bunch of pictures like this of different parts of the sky over the course of a couple of nights, and then come back a few nights later, or a few weeks later, better yet, and take a picture of the same patches of the sky, well, among the 100,000 or so galaxies, there will be some that produced one of these type 1a supernovae, okay? They occur roughly once every few hundred years per galaxy. They're kind of rare. But if you've got 100,000 galaxies, you're going to find a bunch of them. And again, we digitally subtract the old images from the new images. Here's a subset of one of these big things I just showed here. So here's a subset. And here's the subtraction. There's a bunch of noise. Any measurement process necessarily has some noise associated with it. But here, cleverly placed in the center of the square, is something that looks like it might be real. And a Hubble picture a few weeks later shows it as well, with greater clarity, of course. And it brightened and declined in a way that was typical of a type 1a supernova. Takes a few weeks to brighten, a few months to decline. The way to really be sure is to take a fingerprint or a star print. And, you have to get a spectrum. So that's where my main job came, or that's what my main job was. I have access to the 2 biggest optical telescopes in the world, the twin Keck 10-meter telescopes on the Mauna Kea volcano of the Big Island of Hawaii. The geologists at UCLA and Cal and Caltech tell us that it's extinct or highly dormant. Well, they'd better be right, because there's like $1 billion worth of equipment internationally owned, okay, on this highly dormant volcano. And Mauna Loa, just a few tens of miles away, erupts every few decades, and Kilauea at the southeastern end of the island is arguably one of the most volcanically active zones in the world. But they say, no, Mauna Kea has moved off from the hot spot. In fact, there's a new island coming up, Loki or something like that. Those of you in real estate might want to start buying it up. I think it's still a few million years before Loki surfaces, but there's a new Hawaiian island coming up. The Big Island is the youngest in the chain. Anyway, the Keck 10-meter telescopes consist of 36 hexagonal segments arranged in a honeycomb like this to work like a single monolithic mirror, but it was much cheaper to build it this way, and this was the brainchild of Jerry Nelson, at that time a professor at Berkeley. He's now at Santa Cruz. Anyway, with a big piece of glass like this, you can collect a lot of light and spread it out, get a spectrum. Here's Fred Chaffee, a former director of Keck, showing you in comparison with a human how big these segments are. He usually wasn't there when we were taking data. This is just a PR shot. The extra light gathering power of the human pupil adds negligibly to the light gathering power of the glass, okay? So anyway, so we would get spectra of these things, and here you can see the brightness versus the wavelength, and here's a nearby type 1a supernova, and here's one of the ones we studied in the late 90s, and you can see the spectrum looks really quite similar. This little feature here tells us that it's a type 1a. This is due to singly ionized silicon. And, there's a bit of noise, so there's some differences, but basically this is a clear type 1a supernova. So when we get spectra like this, then we're really very happy campers, and you can see now the real reason that we build observatories in Hawaii. I live in the San Francisco Bay Area, and the water there is considerably colder than it is here in LA or Orange County, and so it's too cold to swim without a wetsuit. Anyway, there's good scientific reasons for building telescopes in Hawaii as well. Okay, so let's get to the punchline. Here are 3 spectroscopically confirmed type 1a supernovae marked with arrows. And the punchline is that they're faint. They're really, really faint. Now you might say, well, big deal. They're in these scrawny, faint, distant-looking galaxies. I mean, there you can't even see the galaxy, you know? So you expect the supernovae to be faint, and that's true. But these supernovae look fainter than they had any right to be. The implied distance, if you use the inverse square law, is greater than you would have expected in any self-respecting, well-behaved universe. What do I mean by that? Well, suppose I toss this apple, that's the Big Bang, and suppose the universe were only a second old instead of 13.7 billion years old, okay? So after 1 second, I can measure the height of the apple above my hand. It's some amount. But it's slowed down, right, because of gravity. If Earth's mass were less, then for a given toss, this apple wouldn't slow down as much, and in 1 second it would reach a greater distance, right? Now suppose Earth weren't here at all. Now, I mean, I can't make the Earth go away, but if I were to toss the apple, it wouldn't slow down at all, right? So in 1 second it would get to an even greater distance. But that's it. You can't get to a greater distance than the distance you reach at a constant speed, if the only 2 choices are a constant speed and a slowing down, right? The biggest distance you're going to get to is the distance you get to with a constant speed. But we measured the apples, the supernovae, the galaxies in which they're located, to be at a greater distance than the distance you could reach at a constant speed. So unless something weird is going wrong, what's the obvious conclusion? It's sped up, it's accelerated, right? If I throw this apple and it has a little rocket attached to it and it goes zoom, then in 1 second it can reach a greater speed. So it sounds like we measured the opposite sign compared with what we expected. We expected a deceleration, a slowing down, but we measured an acceleration, as though there's some sort of a weird thing pushing on these galaxies. Now, I can see the gears turning in your minds, and you're saying, well, that's a preposterous conclusion. What if the universe were 2 seconds old? Then obviously the apple gets to a greater distance in 2 seconds, and so that might be a simple solution, right? Well, good try if that's what you were thinking. But it turns out, in detail, the argument is independent of the assumed age of the universe. The supernovae were more distant than expected based on the redshifts of the galaxies. And some of you have studied quite a bit of astronomy and will know what I mean. If you haven't and don't know what I mean, that's okay. Just tell your neighbor the apples were all too far away, okay? But the point is, at a given redshift, which you can measure from the spectrum, you can predict the distance in any well-behaved universe, and the distances were always greater than the prediction. So that turns out to be independent of the assumed age, but this is an easier argument to understand. Okay, so these things were too far away. It looks like the universe accelerated. So the headline that came out shortly after, actually I was privileged for the High Z team to announce this result at a talk at UCLA, actually at Marina del Rey. The headline that came out was "Astronomers See a Cosmic Anti-Gravity Force at Work." We use this term hesitantly because people ask us, well, can we attach this stuff, whatever it is, to our cars and levitate over, traffic jams here in the LA area or in the Bay Area? And the answer is no, you can't attach this stuff to your car. We think it's a property of space that's not harnessable. And even if it's a substance in space which is harnessable, there's only a little bit of it around here. You need like 100 million light years of otherwise empty space to start noticing its effects. And better yet, 1 billion light years, okay? And so we're not going to have machines that are gathering material over, hundreds of millions of light years. So anyway, you can't gather it, and anti-gravity doesn't imply negative mass. It implies something different, okay? Well, the first person on the high redshift team to realize that this is what the data were trying to tell us was a young postdoctoral fellow who was working with us at Berkeley at the time. He was charged with analyzing the data, Adam Rees. He's now a professor at Johns Hopkins University, very famous, and in fact, I'm proud to say, elected to the National Academy the same year that I was, 2009, but he was my postdoc. So anyway, it's really great. I just visited him a couple of weeks ago, and this is from Time magazine, Adventures in Anti-Gravity. And he realized what was going on, and most of the people on the team doubted him at first, but as people on our team tried to reproduce the calculations and the measurements, we kept getting the same answer that he did. And it turns out the other team, Perlmutter's team, was getting about the same answer at about the same time. That was February of '98. By the end of '98, no other astronomers or physicists had found any obvious flaw in what we had done. So the editors of Science magazine proclaimed this to be the single most important discovery in all areas of science in 1998. Now, we were proud of that, of course, but we still weren't sure it's right. But, it takes time to really make sure something is right. Now, 13 years later, we do think it's right. But anyway, they thought it's still worthy of this designation. Now, the caricature of Einstein is surprised here, not because he's blowing multiple universes out of his pipe. You might not have known this, but physicists now think that there may well be multiple universes. That's maybe the subject of some future talk. And they come out of the pipes of theoretical physicists. Okay, that part might not be right. But anyway, instead, Einstein is surprised because this one universe that he blew out of his pipe is expanding faster and faster and faster with time, rather than more and more slowly, as would have been expected. He's doubly surprised because there's a sheaf of papers here under his arm, and it has an equation. The Greek letter lambda equals 8 pi g, Newton's constant, times the density of the vacuum. Now, you might say, who's this guy from Berkeley who was invited to give this talk? What's he talking about, the density of the vacuum? You were taught on your mother's knee that the vacuum is zero, zilch, nothing. How can it have a non-zero mass or energy density? Well, again, I'm just the messenger. This was Einstein's idea. In 1917, shortly after developing the general theory of relativity, which is just a more advanced theory of gravity than Newtonian gravity, he realized that, the universe should be falling in on itself because galaxies are pulling on one another gravitationally, and so unless there's some opposing force, the universe should be contracting. It should be collapsing in on itself. Yet at that time, in 1917, most people thought that the universe is static, neither expanding nor contracting. Hubble had not yet made his discovery, okay? Now, if you have a downward force, but you exactly balance it with an upward force, you can have a static object. If one or the other dominates, then that object moves. So Einstein dreamed up a cosmological constant, a force or an effect of unknown physical nature, never seen in the laboratory, okay, repulsive, and tuned in such a way that it exactly balance the attractive force between galaxies. Now, this was something that was sort of repugnant to Einstein and most other physicists. It seemed finely tuned. There was no experimental evidence for this stuff, okay? It implied that the density of the vacuum was non-zero and repulsive, So Einstein didn't like this, but he felt compelled to introduce the idea. A dozen years later, Hubble discovered that the universe isn't static after all, it's expanding. So the whole physical and philosophical motivation for the cosmological constant, this fudge factor that made the equations less pretty, not wrong, but less pretty, okay, the whole motivation disappeared. And Einstein renounced the cosmological constant anecdotally as the biggest blunder of his career, because had he not insisted on it, he would have predicted, as some of his theoretical friends did predict, that the universe is more likely to be in some dynamic state. So he didn't like it, and he renounced it. So here he is, sad that he ever introduced the idea of the cosmological constant. Now, I don't know that that's what he's thinking, but I'm just suggesting it, okay? What have the two teams done after the better part of a century? They've resurrected the idea of a repulsive effect, okay? But they've made it repulsive, or at least dominant, only at distances that are really big, after a few 100 million light years. So in this room, the down arrow dominates, and in our solar system, the down arrow dominates, and in our galaxy, the down arrow dominates, and in our local group of galaxies, again, attractive gravity, the down arrow dominates. But if you go far enough out and traverse enough otherwise empty space, this substance, I'll discuss it in just a few minutes, builds up enough such that the up arrow dominates, and over the biggest distances, then the universe expands faster and faster and faster. So the whole idea of a repulsive effect, instead of being Einstein's biggest blunder, may have been his greatest triumph. And his blunder was the much more minor one of giving it a mathematical equality with attractive gravity. So if Einstein were around right now, I don't know what his reaction would be, but it might be something like what they had on the cover of Science magazine, okay? Something like this, okay? Again, he died in 1955, so decades before this discovery, but he would have been pleased, I think. Anyway, if this substance is a property of space, we can make some predictions, because the conclusions were drawn based on supernovae that were 4 or 5 billion light years away. So that tells us that in the last 4 or 5 billion years, the universe has been speeding up in its expansion, okay? But it also means that sometime earlier in the history of the universe, it should have been slowing down. Because back when galaxies were close together, not only was their gravitational attraction for each other stronger, but since the amount of space between them was less than it is now, then if this stuff, whatever it is a property of space, and there's not much space between the galaxies, then there's not going to be much repulsion. Okay? So gravitational attraction should dominate over repulsion at some point earlier in the history of the universe. And then eventually, as the galaxies spread apart, not only does their gravitational attraction decline because of the inverse square law of gravity, but also the repulsion increases because there's more space between them, and the cumulative effect of this stuff increases. So my former postdoc, Adam Rees, designed an observational experiment with the Hubble Space Telescope. We found and studied very distant supernovae, 6, 7, 8, even 9 billion light years away. And an analysis of their apparent brightness shows that in the first 9 billion years of its existence, the universe was slowing down. So attractive gravity did dominate, but only in the last 4 or 5 billion years did the repulsive component begin to dominate. Okay? So the universe did slow down for a while. It didn't reverse its motion, but it was slowing down, and now it's starting to speed up. And that kind of a transition from deceleration to acceleration is known as a jerk. I didn't know that until we did this study, but you have position, and the first derivative of position is speed, and the second derivative of position is acceleration. Well, the third derivative is called jerk, okay? I didn't know that, but that's what it is. Ivan, did you know that the third derivative of position is jerk? It is. You'd think jerk is something discontinuous like that, but no, it's just a change in the acceleration. So, in a sense, we measured the cosmos to have gone through a change from deceleration to acceleration. So, in a sense, we measured it to go through a jerk. And the New York Times headline that came out was "A Cosmic Jerk That Reversed the Universe." And here's my former postdoc, Adam Rees. Now, you know how it is with big, thick newspapers. You read the headlines and you look at the pictures. Who has time? Who has time to read through these thick things? You only read the articles of most interest. So people start asking me, hey, who's this jerk you work with who reversed the expansion? Anyway, okay. Well, so what is the stuff? I'm getting near the end because I want to allow some time for questions. It can't be the visible matter of the universe because all visible matter that we know of pulls. And it also can't be dark matter. How many of you have heard of dark matter, right? Okay, yeah, it's a very popular thing to study in astrophysics right now. Dark matter keeps clusters of galaxies like this one bound together. You can see dark matter there and there and there and there. Anyway, well, that's just a joke, but we know it's there, okay, because if there weren't the gravitational attraction of some sort of extra invisible mass, then there wouldn't be these clusters of galaxies, yet they're all over the place. They're not just chance galaxies passing through the night. There's far too many of these clusters, and there are other reasons we know that they're gravitationally bound. So there's dark matter binding them together, and that argument was first made by Fritz Zwicky of Caltech, one of my heroes. I was a graduate student at Caltech, but I arrived just a little bit after his death, so I never met him. But he was decades ahead of his time in many ways. He was a brilliant man, but he wasn't taken very seriously by most of his colleagues because he was arrogant and abrasive, and he didn't think much of the intellectual qualities of his colleagues. And you know, Caltech's a pretty brainy place, so the professors there didn't take these criticisms lightly. I mean, maybe here he's showing what he thinks of the typical brain size of his colleagues. Again, I don't know that that's what he's doing, but it could be. I mean, seriously, he's on record. Yeah, he's on record in having referred to his colleagues as spherical bastards, because you know they're bastards any way you look at them. That's not a good way to make. That's not a good way to make or retain friends. Don't call your friends spherical bastards, okay? But anyway, my own advisor, Wal Sargent, got along with him quite well. But anyway, he came up with dark matter, and I couldn't resist throwing in that tidbit because it's funny. And secondly, dark matter is often confused with the stuff that's pushing the universe apart. So I wanted to make that distinction. Dark matter pulls. It's what keeps galaxies and clusters of galaxies bound together, if anything. It doesn't cause them to spread apart. And you might think that anti-gravity might be due to antimatter, you know, like the opposite of matter. If I shake hands with an anti-Alex, we explode in a burst of radiation. That radiation, however, has a positive attractive gravity, and so does antimatter. So antimatter is not what's causing this effect either. Instead, it's something new, and the term that has been given to it, for better or worse, is dark energy. Dark because we don't see it and it's mysterious, and energy because it's definitely got some sort of an effect there. It's unfortunate, I think, that it was given this term because if there's one equation that lots of people know, what is that equation? E equals mc squared, right? So people ask me, is dark energy the same thing as dark matter? The answer is no. Dark matter pulls, dark energy pushes. So they're definitely not the same thing. But the universe has a lot of this dark energy. Nearly three quarters of the total contents of the universe is this dark energy. So we'd better understand it, okay? I mean, it's a huge, huge problem. What is this dark energy? Perhaps the number one observationally motivated unsolved problem in physics right now is what is the physical origin and nature of the dark energy? And it was first found through these studies of supernovae. Most of the rest of the universe is Zwicky's dark matter. And you know what? We don't know what that is either. We think it's some sort of subatomic particles left over from the Big Bang, and maybe they'll even create some of those with the Large Hadron Collider. By the way, rumors that the Higgs boson has been found are probably premature. Most other scientists working on the project have not yet put their stamp of approval on that rumor. So anyway, but they might produce some dark matter particles, but we still have not detected a single one of them. The only parts of the universe, frankly, that we know of in any detail are this little slice, 4% of the universe, of which only 0.4% is easily visible, stars and planets. The rest is hard to detect intergalactic gas. But anyway, this is the stuff that's made of atoms. The rest, 96%, we know it's there, but we don't know what it is. So we're sort of the afterthought of creation. the debris of the universe. I don't mean to imply you're not important. You are to yourselves and your loved ones and your friends, but you're not made of the dominant stuff of the universe. The dominant stuff of the universe is this dark energy that's pushing it apart, and the dark matter, which in little pockets, it's keeping it together. And this stuff is the only parts that we really understand. So when people say, physics is dead, we don't have anything left to learn, we know it all, you can point out that we don't understand what 96% of the universe is, okay? And for the young people here, you can aspire to try to figure that out. The other reason the dark energy is important is that it may provide a clue to the holy grail of physics, of theoretical physics right now, and that's the unification of the two great pillars of modern physics. Quantum physics on the one hand that deals with the very small, maybe the dark energy as little particles forming out of nothing and then disappearing. And then general relativity, the physics of the very large. They work very well in their own domains of applicability, okay? But when you try to treat a problem with both general relativity and quantum physics, they're completely at war with one another. There's no unified theory. And string theory is one of the things that the most number of physicists are working on right now. Not necessarily true, but it may be true, We just don't know yet. But there are very few testable predictions of all these string theories. Well, dark energy is one of them. Those theories that categorically deny the possibility of a universe filled with dark energy or of a failure of general relativity on large scales. That's another similar but different explanation. In other words, that it could be that there isn't dark energy, but rather that general relativity fails, and hence our conclusion based on general relativity is wrong because we're using the wrong theory. But anyway, any string theory that categorically denies either the existence of dark energy or the failure of general relativity on large scales can be ruled out as a candidate theory for the theory of everything because it doesn't explain an observed fact of the universe, okay? So anyway, a lot of physicists are very excited about this dark energy. Now, you might worry that if the conclusion were based on only just one technique, supernovae, maybe it's flawed. Yes, two, and now many, many more teams have independently confirmed the acceleration effect with supernovae. But what if the technique is flawed? That's a valid concern, and the more important your discovery in science, the more important it is to verify it with completely independent measurements, okay, that have their own sources of uncertainty or whatever. I've run out of time, but let me just briefly mention that in the 13 years since our discovery, it has stood the test of time, and indeed there are now several other measurements that independently lead to this conclusion. One is based on studying the echoes of the Big Bang, the so-called microwave background radiation. It shows that there is almost certainly dark energy because these little tiny variations in density with which the universe was born gradually grew as a result of gravitational attraction into galaxies and clusters of galaxies and voids. And the manner in which they grew depends on the attractive aspects of gravity and the repulsive aspects of this dark energy. And the computer simulations end up with a universe that doesn't look like our observed universe unless you include the effects of dark energy. So that's one of the arguments. And there are other arguments as well. So now in 13 short years, it's gone from you guys are crazy to we now accept that something weird is going on. Let's figure out what's the cause of this weirdness, okay? But it's remarkable how quickly the observations have been accepted, in part because the observed universe looks like these computer models. Okay, well, finally then, what will happen to the universe? How will it end? Well, if it continues to be dominated by a repulsive dark energy, then it'll expand forever, faster and faster and faster. Because the bigger it is, the more the dark energy dominates over the attractive nature of galaxies and dark matter. So if the dark energy remains repulsive, the universe will expand faster and faster with time, a runaway universe. And if you want to look at galaxies and clusters of galaxies with your very own eyes through a telescope, you'd better do it soon, in the next few tens of billions of years, because beyond that, the galaxies will have been whisked away, okay? And that's what we thought would happen 10 years ago when this headline, when this cover story was written was about our work. But since that time, theorists like Andre Linde at Stanford and others have shown that there are possibilities for the dark energy. Since we don't know what it is, every possibility needs to be considered. And there are reasonable possibilities where at some time in the future, the sign of the dark energy changes and it becomes attractive rather than the current repulsion, okay? If the dark energy will someday become attractive, then it's still conceivable that the universe will someday slow down, come to a halt, and then reverse itself into a big crunch. So we haven't yet solved the biggest mystery of the cosmos. We only know that with the amount of dark energy there is right now, the acceleration will probably continue for at least a few more tens of billions of years. But beyond 1 trillion or so, we don't really know, okay? So sorry about that. Anyway, my final slide is one of Robert Frost, the famous American poet, who was well-educated. He may not have known about anti-gravity, but he knew that the universe may either recollapse and end up hot and dense and compressed, kind of like an ending in fire, hot, or that it might expand forever, becoming forever, colder, more dilute, darker, eternal expansion. That's sort of like an ending in ice. Because he had this famous poem, right? Fire and Ice. Some say the world will end in fire. Some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. So you see, Frost would prefer the big crunch universe that becomes hot and compressed. But if he and the universe were to perish twice, then eternal expansion and an ending in ice would be okay with him. And that's perhaps appropriate given his name, Robert Frost. Thank you very much for your attention.